Greetings. In our previous videos, we managed to calculate R properties for different positions of our problem. Now we shall move to simplifying equations and calculating all the processes. Our final problem here with the properties is to calculate properties for point 3, which is here for point 3. Now, what are the properties at point 3 since it's perfect gas? How could we calculate the properties at point 3 as compared to, say, point 2? Of course, what we need is a difference between energies or enthalpies or entropies. If we could do that, then we could also add that difference to the values we already know for points 1, for point 2, and then gain values for point 3. The method for it is somehow complicated, and I don't want to go into that for the time being. What I would do is to assume that the distance between 2 and 3 is perfect gas. So if 3 is perfect gas, I assume 2 is perfect gas, although I know that this would imply 2 to 3% error, but I would do it for the time being. Once we come to calculating real gas effects, then we would learn methods to calculate the error involved in assuming point 2 as perfect gas. Okay, we learn how to calculate it, and therefore it would be fairly easy to add that calculation to the value that we have here. For point 3, we have P3 equals 1500 kilopascals, T3 equals 2878.7 kelvins, and V3 is 0.88568 cubic meters per kilograms. Now, if we assume perfect gas between points 2 and 3, assume perfect gas between points 2 and 3. What would it mean? It would mean that U3 minus U2 would be CV0 times T3 minus T2. Therefore, U3 would be U2 plus this term, and that is, we have U2 2529.1 plus 1.4108, which is CV0 for steam. We know that from the tables, times T3 minus T2, which is 2878.7 minus 393.36, and the outcome for U3 would be 6035.4 kilojoules per kilograms. This is some assumption, a good estimate with perhaps a couple of percent error in it, but as it is, it's a good assumption. So here we could add U3 for point 3, we could add U to be 6035.4. We could also do do a similar practice for H and a similar practice for S. To calculate H, we need to write H3 equals H2 plus CP0 times T3 minus T2. And this would be 2706.2 plus 1.8723 times 2878.7 minus 393.36, and the outcome for H3 would be 7359.5 kilojoules per kilograms. And that's our estimate, our best estimate for H3, which I would just fill in here, 7359.5. How could we do it for S? If it's perfect gas, then S3 minus S2, S3 minus S2 equals CP0 ln T3 over T2 and minus R ln P3 over P2, and therefore S3 would be S2, which is 7.1269 plus 1.8723 ln 2878.7 and divided by 393.36 minus R, which is for steam. It is 0.4615 ln 1500 divided by 200. And the result of this equation for S3 is 9.9236 kilojoules per kilograms Kelvin. So I would just complete my table here. S3 is 9.9236 kilojoules per kilograms Kelvin. And finally, the final property that we know is the availability for point 3. And therefore, A3 would be A3 equals the same equation as we had, U minus U0, which is 6035 minus 62.980 plus P0 times V minus V0, which is 100 times 0.8868 minus 0.001001 and minus 288 times 9.9236 minus 0.2245. And the result of this equation for A3 is 3267.5 kilojoules per kilograms. And I will just fill in the table. 3267.5 kilojoules per kilogram is the value for um, a tree, and therefore, by completing this table, we have uh, done our um, second task, which is just finding properties. You see, what we have done, we have decided on our um, control volume, we have found our properties, and we have drawn our diagram. So we have done these three tasks. What we haven't done yet is to write down equations and simplify it. We just did it once for mass conservation and managed to learn that specific volume remains constant. Now we have to do it, the rest of equations, and see how they would result and what we would learn from them. Now is a good time to simplify the conservation equations for the problem we have. Now, these are the conservation equations, and as we know, there is no mass entering or leaving the cylinder. So these two terms vanish. These two terms also vanish. These two terms vanish. And these two terms vanish. So our equations would, in fact, exclude all terms that relate to incoming and outgoing mass. Now, let's start with the mass conservation equation for processes 1, 2, and also 2, 3. And the answer is very simple, very similar to what we did before. The mass conservation tells us that M0 equals M2 minus M1, and therefore M2 equals M1. As we usually write it, we write first these two terms, so I could write it like this way. M2 minus M1 equals 0, which just shows that I have simplified the left-hand side of the equation. Now, for process 2, 3, still there is no mass entering yet leaving, and therefore, in a similar manner, M3 minus M2 would be 0, and that concludes that M3 equals M2. So these are the equations for the mass conservation law. There's nothing more to it. Now we go to the first law of thermodynamics. Well, as for the first law, let's have a look at the equations. And we know that there is no incoming or outgoing mass, so these two terms vanish. Also, there is no moving boundary, so there's no work in this problem. In fact, as soon as the piston starts to move, our problem ends. So this term would vanish, and uh, all we would have is a change of energy between initial point, second point, and the third point, and the heat transfer that has caused this change of energy. So how we write it? The way we write the first law would be M times U2 minus U1 equals Q1, 2. And for the process 2, 3, we could say M times U3 minus U2 equals Q2, 3. Now, all we need to do is to insert values. So Q1, 2 will equal 0.15 times 2529.1 minus 817.6, and that equals 256.7 kilojoules, and Q23 equals 0.15 times 6035.4 minus 2529.1, and that would equal 525.9 kilojoules. So these are the two um, heat transfers and what we get from the first law of thermodynamics. Now is the turn for the second law of thermodynamics, and what we see here is that these two terms, the incoming mass and outgoing mass, vanish, and we are left with three terms: the change of entropy for the water inside the cylinder, the entropy transfer due to heat transfer from the boundary, which of course has a value. We have a change of entropy, we have some heat transfer, and the other point is the generated entropy. And the two unknown terms that we have is an average boundary temperature and the generated entropy. We have to decide between these two terms. And what does that mean? Now, let's see, let's move to our picture and see what we could say. Well, look, there is a heat transfer certainly from this boundary. Okay, please note that transfer of entropy, which is Q over TB, is different from generation of entropy. And we have transfer of entropy through this boundary. There is some entropy generation here outside because certainly there would be a different temperature between here and here. Okay, there's a different temperature, and so there would be entropy generation outside our boundary, which has nothing to do with the entropy generation if it is inside our boundary. Now, the result of that entropy generation, which is not within our boundary, is that some heat would be transferred through this boundary. Is there any entropy generation inside this one? And the answer is no. At least it's a very good assumption if we assume that there is no entropy generation inside it, because there is no gradient of temperature here. We assume that there is uniform temperature. Always there is uniform temperature inside this boundary, and therefore there is uniform temperature, there is uniform pressure, and there is no mixing, friction. We haven't assumed any of those entropy generating processes, which entropy generating elements that could make a process irreversible. So what you have here inside this boundary is a reversible process. And this would be a good assumption for this. This would perhaps be the best assumption for this problem. I would explain further for you when I simplify the second law of thermodynamics. So, as for the second law of thermodynamics, As for the second law of thermodynamics, we could write that for the first process, the change of entropy inside the boundary that we have selected, which is m times S2 minus S1 equals Q12 over TB, which is the average boundary temperature or the equivalent boundary temperature, because the temperature changes, the boundary temperature changes, and therefore there would be some change of boundary temperature. Now, you see, we could either assume that entropy generation is zero, which is a good assumption, fair assumption, and calculate TB, or alternatively, if we wanted to calculate some entropy generation, we would have to approximate some boundary temperature, which wouldn't be that very good approximation anyway, and it wouldn't give us a very good answer for entropy generation. So this is the best thing we could do with this equation. And the outcome is that TB equals TB would equal heat transfer divided by change of entropy, which would be 256.7 divided by 0.15 times 7.1269 minus 2.56, and I would call it equivalent temperature, because this is not an average temperature, it's an equivalent temperature, is 374.7 kelvins, and I would call this equivalent, because it's not average. The average temperature for this process, which is the sum of the two temperatures, initial and final, divided by 2, may be calculated to be 371.68 kelvins, which is not that far off. You see, if we had assumed that there is some irreversibility that we don't know of and we don't know why, then we would have to assume some average temperature, and we would have calculated a value, and the value I calculated was negative, which is, of course, renders the process impossible, which is not true, which is not correct, but this is a value which is quite justifiable. For the other process, 2,3m times S3 minus S2 equals Q23 divided by TB, and this was TB between 1, 2, and this is TB between 2, 3, and the outcome for TB would be 525.9 divided by 0.15 times 9.9236 minus 7.1269. You see, it's very easy. Once you have calculated all properties, it would be very easy to just insert them into the first law, second law, and calculate all work, heat transfer, or entropy generation. But you have to, of course, be careful on how you apply these values. And TB between 2, 3, and this is again equivalent, would be 1253.6 kelvins. And here we see the point that since the temperature difference is very high, the average temperature, this was average TB, and the average temperature, which is just the sum of the initial and final temperatures divided by 2 would be between 2 and 3. The average temperature is um, T3, which is 2878.7 plus 393.36 and divided by 2, and the average temperature would be 1636.03 kelvins. And you see that the difference between these two values is quite high because the difference in temperature is quite high, and there's just no justification to assume that an equivalent temperature is equal or even near the average temperature. The final step in this very long problem is to calculate the availability equation. What does this availability equation tell us? It tells us that the change of availability inside our boundary, whatever it is, equals the availability that enters with inlet mass, the availability that leaves with exit mass, the availability transfer with heat transfer, the availability transfer with work or changing boundary or moving boundary, and the irreversibilities. How did we calculate this equation? Very simple. We just combine these two equations to reach to this equation. It is just telling us that it is just very simple. You see, with this equation, we said that the change of mass within a controlled volume is the inlet mass minus outlet mass with no coefficients. With energy, the change of energy within a controlled volume was the energy entering with the inlet mass. So that was the energy was multiplied by inlet mass, the energy leaving with the exit mass, and there were two further terms, heat transfer and work. Both had coefficients of 1 in SI units. So this is the first law of thermodynamics. What does the second law tell us is that the change of entropy within our boundary, our control volume, equals the entropy that enters with inlet mass, the entropy that leaves with exit mass. And there are two terms. There's no sign of work. There are two terms. One is heat transfer, and its coefficient is 1 over Tb. The heat transfer coefficient in this equation was 1. Here the coefficient for heat transfer term is 1 over Tb. And there's a new term, Sgen. You see, there are three terms which show the process, which define the process. One is heat transfer, one is work, and the other is Sgen. In the first law of thermodynamics, we have heat transfer, we have work, there is no Sgen. In the second law of thermodynamics, we don't have work, it's heat transfer and Sgen. This equation, since it's a combination of these two laws, has all terms together. So it has dACV by dt, which basically is telling us that it is the change of availability inside our boundary. It is this term. You see, it is this term. A, the A that we have there on the left-hand side of that equation could be calculated just like this, and it is this term. So the change of availability inside our control volume equals availability that enters with the mass that enters. And this availability here is just this term here. You see AF, this term here. So this is calculated like this one. You see, this term is energy. So it's U. This term is availability, which would give you some equivalent of U, which is A. This term is energy with the flowing mass, which is H. And this term is the flow availability, which somehow replaces this one. So the change of availability inside our control of volume is the availability that enters with mass that enters, the availability that leaves with the mass that leaves, availability transfer with heat transfer. You see here, heat transfer had coefficient 1 over TB. Here, it has the coefficient 1 minus T0 over TB. So it has a different coefficient. Here, we didn't have any heat transfer. The coefficient was 0. Here, the coefficient was 1. Here, the coefficient is 1 over TB. And here, this is the coefficient. Work appears here, which is this term, and its coefficient was 1 here, and it's 1 here as well. You see, availability is defined in terms of work. So it's no surprise that the coefficient of work should be 1 here. The change of boundary, what does it show us? This term shows us how much availability is reserved in the surrounding. You see, when a piston rises, it saves some availability in the surrounding. And when it is returning to its ambient condition, it just takes back that availability from the surrounding. When you inflate a balloon, what do? You just save some availability in the surrounding. If you empty the balloon, the surrounding gives back that availability to the balloon and in fact does work on the balloon to let air out. So this term just shows the availability saved in the ambient. And this term is called irreversibility. This is entropy generation times T0, which is the ambient temperature, and this is irreversibility. To simplify this equation for this problem, we assume that there is no entropy generation, so this term vanishes. There's no boundary movement, so there's neither work nor change of boundaries. So these three terms, work, change of boundary, and which is these two terms are in parentheses, which because both are some sort of work. This is T0 times S dot gen, which is irreversibility. This is 0. These two terms vanish because there is no mass that enters or leaves. So our equation would just simplify to the change of availability equals the availability transfer with heat transfer. And that's exactly what we would do, how we would calculate it. Now, availability equation. So it is M times A2 minus A1. This is for process 1, 2 equals 1 minus T0 over TB times Q1, 2. replace values in this equation, and it would be 0.15 times 566.7 minus 170.46, and that equals 1 minus 288 divided by 374.7 times 256.7, and the left hand side is 59.436, and the right hand side is 59.4, and the equality checks. You see, for the availability equation, since we have all terms, we have calculated all terms in the previous two laws, then we should be able to calculate all terms here. And we just have to check if they equal. It means that all our previous calculations were correct. And if it's not equal, then you should look for some errors. It's a very good practice to check errors, regardless of what it means. The meaning is very good, but there's a lot of meaning to it. But as it is, one side benefit from this equation is that we know that we have calculated everything right. For process 2-3, it is m times A3 minus A2, and that equals 1 minus T0 over TB times Q2, 3. And you calculate is 0.55 times 3267.5 minus 566.7, and that equals 1 minus 288 divided by 1253.6 and times 525.9, and the outcome, the left hand side, is 405.12, and that should equal 405.1, and the equality also checks here. Well, this is a classic way of solving these problems. We could go step by step, calculating properties, drawing the diagram, writing our equation, simplifying, and then collecting everything to get the answer. And all of these things should be done after we have decided on where our boundaries are. Well, thank you very much for watching this problem, and cheers.